Imagine a place in the universe where time stretches like taffy, where light itself tries to leave and simply fails. Imagine falling toward that place and discovering that from your point of view, nothing unusual happens when you cross the point of no return, yet from far away you seem to freeze on the brink forever. We call that place a black hole, the ultimate one-way door, a cosmic trap from which nothing can escape. And yet, according to Stephen Hawking, black holes do slowly lose energy and even evaporate. How can something defined by inescapable gravity leak? If that claim is true, then our basic picture of what black holes are has to change, and tonight we're going to push on that picture until it bends.
Before we tackle evaporation and paradoxes, we need a solid mental model of what a black hole actually is and what it is not. Popular culture shows them as hungry whirlpools that roam through space, gobbling up anything in sight. That image is dramatic, but misleading in almost every way that matters. A black hole is not a cosmic vacuum cleaner that sucks from a distance. It is simply a place where matter has been squeezed so tightly that gravity takes over completely. To understand why that is so extreme, we can start with something much more familiar, a star like our Sun. A normal star is a long-running compromise between two opposing forces. On one side is gravity. All the atoms in the star pull on one another and try to collapse inward. On the other side is pressure from nuclear fusion in the core, where hydrogen is fused into helium and energy is released. That energy heats the gas and makes it push outward. For billions of years, the star balances between falling in and pushing out. It is like a gigantic, self-adjusting bridge between gravity and light. Eventually, though, that balance fails. For a small star, gravity wins gently. The outer layers puff away, and the leftover core shrinks into a white dwarf, a hot, dense ember with the mass of a star packed into something the size of a planet. Gravity squeezes the electrons into a tight lattice, and their quantum pressure holds the star up. For a slightly heavier star, gravity keeps pushing. The electrons and protons are crushed together into neutrons, and the star collapses further into a neutron star, where a mass greater than our Sun is packed into a ball only about as wide as a city. At that point, matter is about as dense as atomic nuclei, and neutron pressure becomes the new support. It is like taking the entire population of Earth and stuffing them into a single teaspoon. If the star is still more massive, even that is not enough. There is no known form of pressure that can resist its own gravity. Nothing pushes back. When that happens, the core of the star collapses in a catastrophic rush. The outer layers explode outward as a supernova, and the core keeps falling inward until the equations of general relativity say that it has reached a state of pure collapse. This is where the idea of a singularity appears. In the mathematics, the collapsing matter forms a region where density and curvature go off the charts. We call that idealized endpoint a singularity, a place where our current theories simply stop being able to describe what is happening. Around that singular core, there is a critical boundary in space, a kind of surface with no substance of its own, defined only by gravity and light. This is the event horizon, the point at which escape becomes impossible. You can think of the event horizon as the speed limit turned inside out. Far from the black hole, if you want to escape its gravity, you just need to move fast enough. Near Earth, that escape speed is about 11 kilometers per second.
For the Sun, it is much higher, but still less than the speed of light. At a certain distance from a collapsed star, the escape speed reaches the speed of light itself. That distance marks the horizon. Once you're closer than that, there is no path, no clever use of rockets, no amount of energy that gets you back out, because that would require you to outrun light itself. This sounds absolute and brutal, and in one sense it is. In another sense, it is more subtle than the monster images suggest. If you replaced our Sun with a black hole of exactly the same mass, Earth would keep orbiting almost exactly where it is now. The day length would not change. The year length would not change. The overall pattern of the solar system would look the same.
The black hole would be terrifying up close, but from a distance it behaves like any other object with the same mass. The danger lies in getting too close. Time plays a strange role near that critical boundary. Einstein's general theory of relativity tells us that mass and energy curve spacetime, and that curvature tells matter and light how to move. One consequence is gravitational time dilation. Clocks lower in a gravitational field tick more slowly than clocks higher up. It is not that they run badly, it is that the very rate of time is different. This effect is tiny on Earth, but we already account for it in the timing of global positioning system satellites. Near a black hole, that gentle difference becomes extreme. If you were to hover with impossibly powerful rockets just outside the event horizon, your clock would tick much more slowly than a clock far away. To you, nothing about your watch would feel strange. Every second would sound like a second, but a distant observer would see your seconds dragging out, stretched by the intense gravity. If you were to drop an object toward the horizon and watch it from far away, you would see it falling more and more slowly, redshifting, fading, and never quite crossing the edge. This leads to a strange picture where there are two overlapping stories about the same fall. For someone actually falling in, the crossing of the horizon happens in a finite time, and nothing special is felt at that exact location. For someone observing from a safe distance, that crossing never quite happens. The object seems to freeze and dim, like a ghost trapped on the brink. Both views are valid within their own frames. Reality has room for both perspectives at once, which is unsettling until you get used to thinking in relativity's language. All of this was theory for a long time. Einstein himself was skeptical that nature would actually create objects as extreme as black holes. The first hints that they might be real came from places where we did not see anything at all. In the 1960s, astronomers began detecting powerful sources of X-rays in the sky. X-rays are high-energy light that does not penetrate the atmosphere well, so we needed rockets and satellites to see them.
One of the brightest of these mysterious sources was in the constellation of Cygnus, the Swan. It became known as Cygnus X-1. At first, Cygnus X-1 was simply a bright but fuzzy point. As telescopes and techniques improved, astronomers realised that the X-rays were coming from a small region orbiting an ordinary-looking blue supergiant star. They measured how that visible star wobbled as it moved, tracking its orbit as if it were tied to an invisible partner. From the timing and size of the orbit, they could estimate the mass of the unseen object. Whatever was pulling on the star was many times more massive than the Sun, yet it emitted no visible light. There are only a few options for such an object.
It could be a cluster of smaller things, like a hidden clump of stars, but that would either spread out or start to shine on its own. It could be a single compact star, like a white dwarf or a neutron star, but the mass estimate rules that out. White dwarfs and neutron stars have upper mass limits. Beyond those limits, their internal pressure cannot hold them up. Cygnus X-1's invisible partner is above that threshold. The simplest explanation left is that it is a stellar mass black hole, feeding on gas from its bright companion. The way it feeds is as important as the fact that it is there at all. Gas flows off the supergiant star and spirals toward the dark object. It does not fall straight in, just like a planet in orbit or water swirling toward a drain. It carries angular momentum, a measure of its tendency to keep going around. As it spirals, it forms a flattened whirl of superheated gas called an accretion disk. In that disk, matter rubs against matter. Friction and magnetic fields tangle everything together, and the gas heats up to tens of millions of degrees. At those temperatures, it shines fiercely in X-rays. That is why black holes are rarely completely black. The hole itself does not emit light from within the horizon, but the material just outside can become one of the brightest objects in the universe. When we point X-ray telescopes at Cygnus X-1, we are not seeing the hole, we are seeing its dinner, glowing in pain as it spirals in. If you picture that system in your mind, you have a giant blue star, a tight orbit, and a tiny invisible point that is heavier than the star itself, wrapped in a hungry, radiant disk. Cygnus X-1 turned out to be only the first member of a long and growing list of black hole candidates. In other systems, similar wobbles and X-ray signals show up. Over time, astronomers have become more and more confident that we are not just seeing exotic stars, but true black holes. They come in different sizes. Some are a few times the mass of the Sun. Others, in the hearts of galaxies, are millions or even billions of times as massive. Despite the range in size, they all share the same basic structure. Mass collapses, an event horizon forms. Outside that horizon, infalling matter heats and glows. If you have ever seen the now famous image from the Event Horizon Telescope, the blurry orange ring around a dark centre in the galaxy Messier 87, you have seen what happens when we push this idea to its limit. That image is not a photograph of a hard surface. It is a map of light skimming around the black hole, bent by intense gravity, and of the glowing gas in the disk. The dark centre is the shadow cast by the event horizon on that glowing backdrop. Even with our best instruments, the hole itself remains unseen. It is defined by absence, by what cannot escape. There is a quiet power in that. Most objects in astronomy are discovered because of the light they send us. Black holes are discovered by what they hide, distort, and shred. They bend the paths of stars.
They twist light into rings and arcs. They turn the normal logic of time on its head near their edges. We identify them not by catching them directly, but by reading the scars they leave on their surroundings. It is like trying to learn the shape of a predator by studying footprints and claw marks on trees. For many decades, this was the whole story. Black holes were one-way doors. Matter and information could go in, but nothing could come out. They were perfect cosmic sinks, growing slowly as they fed on gas, stars, or unlucky clouds that wandered too close. You could treat them as the simplest objects in the universe. Once you knew their mass, spin, and electric charge, everything else about them did not matter. That simplicity was appealing. It made a wild universe feel a little more orderly. Then the quantum world crashed the party. When Stephen Hawking sat down to think about what would happen if you took general relativity's curved spacetime and added the churning, restless fields of quantum physics near an event horizon, he found something shocking. The perfect darkness developed a faint glow. The simple one-way door began to leak. Energy seemed to seep away from the region around the horizon, as if the curvature itself was paying a slow tax. If you have ever looked at a calm pond and then zoomed in with a microscope to reveal a swarm of tiny life, you already have the intuition we need next. The region around a black hole looks empty in the everyday sense. It is space where most matter has already fallen in or been flung away. But in quantum physics, empty is never truly empty. There is structure hidden in the nothing, and when that structure meets an event horizon, strange things begin to happen. As we move deeper into this story, keep two images side by side in your mind. One is the classical picture of a black hole as a simple well in space-time, a region that swallows and never returns. The other is a more restless, buzzing picture where even empty space is alive with activity. The real key to understanding how a black hole can evaporate lies in what happens when those two pictures collide. The collision between those two pictures begins with a simple question.
What does it even mean to see something that, by definition, does not let light escape? You and I are used to seeing objects because they bounce light toward our eyes or toward our telescopes. If an object never sends light out, then there is no direct image to collect. A black hole is exactly that kind of object. Once light crosses the event horizon, there is no path that curves back out into the wider universe. It is not just hard to look inside, it is causally impossible. So if we cannot look in, how do we know what these things look like at all? The answer is that we cheat a little by using the universe itself as a camera. Light that skims near a black hole can be bent into new paths without ever crossing the horizon. In Einstein's view, gravity is not a force pulling on light from a distance. Instead, the presence of mass curves space-time, and light simply follows the straightest possible paths through that curved geometry. Those paths are called geodesics. Near a black hole, geodesics can loop, twist, and wrap in ways that our everyday experience never prepares us for. Some light falls in, some light escapes, some light gets caught in delicate orbits right on the edge. Just outside the event horizon, there is a region where light can, in theory, circle the black hole many times. This is sometimes called the photon sphere. Imagine firing a beam of light across the surface of a world so curved that the beam just keeps looping around. In practice, these orbits are unstable. A tiny nudge inward, and the light is lost forever. A tiny nudge outward, and it spirals away into space. Still, the existence of this region means that even light that never falls in can spend time in the grip of the black hole, and that shows up in what we eventually see. If you put glowing gas around a black hole, as nature often does, light from that gas will take many different routes to reach us. Some rays skim close to the horizon and get whipped around. Others pass farther out and are only gently deflected. When all of these paths are added together by our telescopes, they produce a distinctive pattern. There is a dark central area where no light can come from, surrounded by a bright, warped ring formed by light that has taken long, twisted journeys near the photon sphere. That ring is not the black hole itself. It is a kind of halo of last chances. The Event Horizon Telescope, a planet-sized virtual instrument made by linking radio dishes across Earth, used this effect to create the now famous image of the black hole in the galaxy Messier 87. It did not zoom in with a gigantic mirror. Instead, it combined the timing of signals collected on opposite sides of our planet to reconstruct how radio waves were being lensed by the spacetime around the black hole. The result looks like a blurry orange donut with a darker centre. That centre is the shadow cast by the event horizon on the glowing gas behind and around it. Even at that level of detail, the horizon itself is only visible as an absence. There is a subtle point here that is worth holding on to. The event horizon is not a physical membrane or a solid surface. If you were somehow falling in, you would not splat against a wall of any kind at that exact location. The horizon is more like an invisible boundary in the geometry of space-time, a place where all possible future paths point inward. From your perspective as the falling traveller, crossing it is uneventful. From the perspective of the outside universe, nothing that crosses ever sends back a signal. Both stories are true inside their own frames. The horizon's reality is defined by what information cannot do, not by what matter feels. To get an intuition for this, think about sound instead of light. Imagine a waterfall so powerful that once you go over the edge, the current is stronger than any swimming stroke you can possibly manage. Upstream of the edge you can still paddle and change your fate. Downstream, no amount of effort changes your eventual plunge. There is a line somewhere in the river where the flow speed matches your maximum swimming speed. That line is not a wall, but it has teeth. Cross it going downstream and there is no going back. An event horizon is like that line, but for light and information, not water and swimmers. The strange way time works around this boundary is another key to why black holes look the way they do. You saw earlier that a clock near a massive object ticks more slowly than a clock far away.
Near an event horizon, that difference becomes so extreme that to distant observers, infalling material seems to slow almost to a stop as it approaches the edge. The light it sends out climbs out of a very deep gravitational well. Climbing out steals energy from the light, stretching its wavelength toward the red and eventually beyond the visible. From far away, the last signals from the falling object fade into darkness, stretched and dimmed until they vanish. If you were making a movie of something falling into a black hole, you could do it two ways. From the falling object's perspective, the story is quick and smooth. It crosses the horizon and heads inward. From the outside, your movie slows more and more as the object approaches the horizon. You never actually see the moment of crossing. Instead, the image hangs there, dimming and reddening, its final frame spread over an infinitely long time. This discrepancy is not a bug in the theory. It is exactly what relativity predicts. Our universe does not give everyone the same version of time. So when we say that black holes are black, we mean that in two overlapping senses. Anything that falls in produces its last easily visible light just outside the horizon, then fades away as that light loses energy. And anything that has already crossed the horizon is cut off from us forever by the structure of space-time itself. That combination of perspective and geometry makes direct images almost hopeless. To truly see black holes, we have to look not at them, but at the way they disturb their surroundings. In a way, we're always looking at their shadows, never at the actors casting them. Those surroundings can be ferociously bright. Remember the accretion disk around Cygnus X-1? Gas there is squeezed and stirred as it spirals inward. Friction and magnetic turbulence pump energy into the particles. They rattle around at enormous speeds and collide again and again. At tens of millions of degrees, the disk does not shine mainly in visible light. It radiates strongly in higher energy wavelengths like X-rays. Our atmosphere blocks most of those, which is good for life but inconvenient for astronomy. To see them, we loft instruments into high-altitude balloons, rockets and satellites. When you look at the sky with an X-ray telescope, the view is almost unrecognizable compared with what you see in visible light. Calm-looking regions in ordinary images become peppered with sharp, intense points. Some of those points are the remnants of exploded stars. Others are neutron stars or white dwarfs feeding on companions. A significant fraction are black hole systems, where an otherwise quiet-looking star is being slowly stripped, its outer layers funneled into a disk and heated to the point of X-ray brilliance. Each one of those is a beacon that says there is a massive, compact, invisible object here that is bending space. The combination of orbital motion and X-ray emission lets astronomers measure both mass and behaviour.
By watching how quickly a visible star orbits the hidden companion and how far it moves, you can work out the mass of the invisible partner. By tracking how the X-ray brightness flickers, you can infer how compact the hot region is. Rapid, irregular flashes suggest a small, dense source rather than a wide, diffuse cloud. Over and over, the numbers point to objects that are too massive to be neutron stars and too small to be star clusters. They point to black holes. On larger scales, the same logic reveals the monsters in galactic centres. Many galaxies, including our own Milky Way, show signs of a supermassive object at their core. In our galaxy, we see stars whipping around an unseen point near a radio source called Sagittarius A star. Some complete tight, fast orbits in only a few years. From those orbits, we can deduce that there is a mass of millions of suns squeezed into a region smaller than our solar system. No known arrangement of normal matter is stable under those conditions. The simplest and widely accepted explanation is a supermassive black hole. When the central black hole has an active accretion disk, the effect can be spectacular. Matter falling in releases an enormous amount of energy as it loses gravitational potential and crashes through the disk. In some cases, that power outshines the entire rest of the galaxy. We see those cases as quasars, apparently star-like points that are in fact the blazing cores of distant galaxies where a supermassive black hole is violently feeding.
The fact that quasars are so bright across vast distances is another way we know that black holes, despite their name, can be the engines behind some of the brightest beacons in the cosmos. All of this is still classical physics. Gravity curves space-time. Matter follows the curves. Light traces out the structure of that curved geometry. Black holes are places where that curvature goes so deep that no light from within can climb out. The event horizon is the boundary of no return. We can map the region around it by following light that just misses, that skims, that circles and escapes. We can weigh the whole by watching the dance of stars and gas around it. We can even, with enough patience and clever engineering, sketch the silhouette it casts on its own glowing environment.
Yet if we stop here, we are left with a picture that is powerful, but incomplete. In that picture, once something crosses the horizon, its story ends as far as the outside world is concerned. The black hole grows or spins faster, or both, but never gives anything back. There is no mechanism for leakage, no evaporation, no glow from the edge. Your intuition might already be whispering that this feels too clean. Nature is rarely that absolute, especially where gravity and the quantum world overlap. That is the next step in our journey. We have built a mental image of the event horizon as a one-way surface defined by the geometry of space-time and traced in light we can see. We have learned how to read the X-ray screams of matter that is doomed to fall in. We have watched stars orbit invisible anchors and have used those motions to weigh the darkness at the centre. All of that gives us confidence that black holes are real, physical objects, not just mathematical curiosities. But there is still that nagging claim from Hawking that these objects are not perfectly black after all. If that is true, then somewhere in this picture there must be a loophole, and to find it, we have to turn our attention away from the glaring glow of accretion disks and look more closely at something that seems much quieter, the so-called emptiness of space itself. When we talk about empty space, most of us picture a kind of cosmic nothing. No stars, no gas, no dust, just a dark void. That idea feels so obvious that it is hard to even see it as an assumption. Of course, nothing means nothing, but physics has a habit of taking obvious ideas and turning them inside out. When researchers began to combine quantum mechanics with fields spread across space, they found that the emptiest place you can imagine is not a blank stage. It is more like a restless ocean, whose surface usually looks flat from far away. To get there step by step, start with something concrete. Imagine a guitar string stretched between 2 points. If it is perfectly still, we might be tempted to say there is no sound. But the potential for sound is already there, encoded in the string and the air around it. Pluck the string, and ripples travel along it. Those ripples are what we hear as notes. Change how you pluck it, or where, and you get different patterns of vibration.
Even when the room feels quiet, tiny motions are still present, too small and disordered for your ears to pick out. Quantum physics extends that idea in a radical way. In the modern view known as quantum field theory, every type of particle is an expression of an underlying field that fills all of space. There is an electron field, a photon field, and so on. Particles are not tiny billiard balls rattling around in emptiness. They are quanta, packets of excitation in these fields. An electron is like a small, localized ripple in the electron field. A photon is a ripple in the electromagnetic field. The vacuum is not the absence of the field. It is the field in its lowest energy state. So what happens if you try to make that lowest energy state perfectly calm?
Here is where a key idea of quantum mechanics steps in. Heisenberg's uncertainty principle tells us that certain pairs of properties cannot both be known, or even defined, with unlimited precision at the same time. The more tightly you pin down a particle's position, the less well-defined its momentum becomes. The more precisely you know its energy at a given moment, the looser your knowledge of how long that energy lasts. Translated into the language of fields, that principle means the vacuum cannot be totally still. If you forced every field to be exactly flat, with exactly zero energy everywhere at once, you would be violating the limits that quantum mechanics sets on how well-defined that energy can be. The fields are compelled to fluctuate.
On very short timescales, the energy of the vacuum can jiggle, as long as those jigs and jags average out in a way that keeps the uncertainty rules intact. Emptiness becomes a restless balance, not a frozen void. Physicists often visualize these fluctuations as pairs of particles and antiparticles that pop into existence for a brief moment and then annihilate each other again, returning their energy to the vacuum. It is important to be careful here. These are not little bullets blinking in and out in a classical sense. They are more like mathematical bookkeeping for how the field behaves when you try to calculate its influence. Still, the image of pairs appearing and disappearing is useful, as long as we remember that they are a way of talking about ripples in a continuous sea.
You might reasonably ask whether this is just a fancy metaphor. Does the vacuum really do anything you can measure, or is this all abstract math? One striking answer comes from a thought experiment turned real experiment, involving two metal plates placed very close together in a vacuum. This setup is known as the Casimir effect. The idea is that the quantum fields between the plates cannot fluctuate in quite the same way as the fields outside, because the plates create boundary conditions that only allow certain modes of vibration in the gap. When you work through the math, you find that the allowed fluctuations between the plates are slightly fewer than the ones outside. That imbalance means the vacuum energy between the plates is a little lower than outside.
The result is a tiny net pressure pushing the plates together, even though there is no ordinary matter or radiation between them. This force is unimaginably small on everyday scales, but with sensitive equipment in a laboratory, it can be measured. In that sense, the vacuum really does behave as if it has structure and energy, even when everything else has been stripped away. Another example comes from the way atoms interact with their own electromagnetic fields. If you take a simple picture of an electron orbiting a proton, it predicts certain energy levels and therefore certain colours of light that the atom should absorb or emit. When you actually measure those lines with high precision, they are slightly shifted, accounting for the interaction between the electron and the fluctuating electromagnetic field around it. That is, the vacuum corrects the prediction and matches the observations. Once again, emptiness shows up as an active participant. By this point, our picture of empty space should feel very different from the simple nothing of intuition. We now have a stage filled with fields that never fully sleep, fields that can push plates together and subtly tweak the energy levels of atoms. On large scales, those fluctuations average out so well that the vacuum looks calm. On small scales, and in the presence of boundaries or strong fields, its hidden activity leaves fingerprints that we can measure. This is the environment in which a black hole lives.
Its event horizon is not cutting into a dead void, but into something more like a sea of restless potential. This is exactly the kind of place where we should expect surprising effects. In physics, boundaries matter. When you have a medium that can vibrate in many ways, like air, water, or a quantum field, the introduction of a new boundary changes which vibrations are allowed. Think of a flute compared with a long, open pipe. Both carry sound, but their shapes pick out different resonant notes. An event horizon is a weird sort of boundary. It is not a physical wall, yet it divides space-time into two regions with very different fates for light and information. Stephen Hawking's key insight was to ask what happens to the quantum fields that pervade space when you place an event horizon into that space and let it sit there. The horizon divides the field modes into those that are entirely outside and can communicate with distant observers, and those that are partly or wholly inside and can never send signals out. The vacuum state that looks calm and lowest energy to someone far away is not the same as the vacuum state that would look calm to someone who is falling through the horizon. This mismatch matters. In quantum field theory on curved spacetime, the definition of what counts as no particle is tied to how an observer measures time and energy. Different observers can disagree about whether the field is empty or full of excitations. Near a black hole, an observer at rest far away, looking at the field outside the horizon, and an observer freely falling across the horizon will slice up space-time in different ways. Hawking found that when you translate between these viewpoints, what looks like vacuum to the falling observer looks like a thermal bath of particles to the distant one. You can think of the horizon as entangling the field modes on either side. Pairs of modes are correlated in such a way that the overall state is still vacuum in a global sense, but if you only have access to the outside region and you ignore the inside, the state you see is mixed, like a warm gas. The distant observer interprets this as real particles being present outside the black hole.
Those particles form what we now call Hawking radiation. They carry energy away to infinity. Where does that energy come from? Energy cannot just appear from nothing. The calculation shows that to keep the books balanced, the black hole itself must lose mass. Remember that in relativity, mass and energy are two ways of describing the same thing. As the quantum fields around the horizon evolve, their configuration shifts in a way that allows some of their energy to leak out as real radiation. That energy is ultimately drawn from the gravitational field of the black hole. The mass of the hole shrinks in tiny steps as the radiation streams away. The popular picture of particle pairs being created just at the horizon, with one falling in and the other escaping, is a story built on top of this deeper math. In that story, the escaping partner becomes real and carries positive energy away, while the infalling partner effectively has negative energy relative to the outside world and reduces the mass of the whole. It is a useful way to think, as long as we remember that the true description involves the whole quantum field and the way it is curved by space-time, not literal marbles being exchanged. What matters for us is the consequence. Black holes are no longer perfectly black. A stationary, non-rotating black hole in empty space will emit a very faint thermal spectrum of particles, like a body with a certain temperature. The smaller the black hole, the hotter this radiation would be. For black holes with masses comparable to stars or greater, the Hawking temperature is unimaginably low, far below the temperature set by the cosmic microwave background, the relic glow of the early universe. That means that in practice, those holes absorb more radiation from the universe around them than they emit, at least for now. In the far future, when the universe has expanded and cooled enough that the background radiation drops below the Hawking temperature of existing black holes, the balance will flip. Then black holes will slowly lose energy on net, shrinking over mind-boggling timescales. As they shrink, they get hotter, which increases the rate of radiation, which shrinks them faster.
The process accelerates until the black hole reaches a tiny mass and, according to the standard picture, ends in a brief, intense burst of energy. That is the ultimate consequence of letting quantum fields and curved spacetime interact at an event horizon. It is worth pausing and feeling how strange this is. We started with the idea of a black hole as a one-way door from which nothing escapes. We now have a mechanism, rooted in well-tested principles of quantum field theory, that predicts a slow leak of energy from the region around the horizon. No information or matter travels out from inside the horizon. The leak is a property of the curved space outside. Yet the effect is real enough that it would, over a very long time, completely erase the black hole itself. You might wonder whether we have ever seen Hawking radiation directly. The honest answer is no, not from astrophysical black holes. The effect is simply too weak against the current warmth of the universe. But the same mathematics that predicts it also underpins many other quantum field phenomena that we have successfully tested. And researchers have built laboratory systems that mimic some aspects of horizons, such as sonic black holes, where sound waves cannot escape from a flowing fluid. In some of those systems, analogues of Hawking radiation have been reported, tiny ripples that behave just as the theory predicts. Whether or not those analogues are perfect matches is still debated, and it is healthy to keep some skepticism, but taken together, the theoretical arguments and the supporting experiments make a compelling case that the vacuum around a black hole is not quiet. It glows, very faintly, with a thermal whisper pulled from the structure of space-time itself. If that picture is right, then the story of a black hole is not just a tale of growth through accretion and mergers. It is also a tale of slow, inevitable loss. This revelation creates new puzzles. If a black hole can evaporate entirely, what happens to the information about the matter that fell in? Does it vanish as well, violating what many physicists believe is a fundamental rule that information is never destroyed? Does it somehow leak out encoded in the Hawking radiation in a way we do not yet fully understand? Or does the final stage of evaporation involve new physics that we have not yet discovered? These questions have driven decades of debate and have tied together ideas from gravity, quantum theory, and even the holographic principle. We are not going to solve those deep puzzles here, but they point to an important lesson. When you take the restless vacuum of quantum fields and the warped geometry of a black hole and let them interact, you get a world that is far less simple than the early picture of a perfect one-way door. Black holes radiate. They lose mass. They may one day vanish. In the process, they force us to rethink what we mean by matter, energy, and even reality itself.
To get a better grip on that rethinking, we need to step back from the horizon and look again at the relationship between gravity and motion. Relativity tells us that free fall is not really falling in the old sense. It is the natural, straightest path through space-time. That idea will turn out to be crucial when we ask whether mass is the cause of curvature, or whether curvature, in some sense, defines what we call mass. Gravity in Einstein's picture does not start with a force pulling objects down. It starts with the simple observation that if you are in free fall, you feel weightless. In a falling elevator with the windows closed, a dropped ball floats beside you. In a rocket drifting in deep space with the engines off, you feel the same kind of weightlessness. Einstein took this seriously. He suggested that freefall is the most natural state of motion, the one that reveals the true shape of space-time. What we call gravity is what it feels like when we try not to follow that natural path, when we stand on the ground and the floor keeps shoving up against our feet. Once you accept that, The next step is to say that mass and energy curve space-time, and that free-falling objects simply follow the straightest available path through that curved geometry. Those paths are called geodesics. A planet orbits a star not because an invisible force tugs on it, but because the space-time around the star is shaped in such a way that this looping path is the straightest option. Seen this way, the familiar phrase mass tells space-time how to curve and space-time tells mass how to move is not just poetry. It is a compact summary of the rules. A black hole is what happens when that curvature is pushed to an extreme. The geodesics near the collapsed mass bend so sharply inward that all paths within the event horizon lead deeper in. Inside, there are no routes that climb back out to the wider universe. The horizon itself is simply the border between those two regimes, the outer surface of no return. Up to this point, all of that sounds one way. Matter shapes curvature, curvature dictates motion, and that is the end of it. Hawking's calculation throws a twist into that story. It suggests that the shape of space-time around an event horizon can, in a sense, give energy back. To see how, it helps to revisit the idea of waves and boundaries. Picture a long, still pond on a windless day. If you tap the surface, ripples spread out. If you erect a barrier with a narrow gap, only certain ripples fit smoothly through that gap. Others reflect or interfere. Now imagine the pond is the quantum field that fills space, and the barrier is not a physical wall, but the geometry created by a black hole. The event horizon and the curved space-time around it change which wave patterns can exist smoothly from one region to another. In flat, empty space, the vacuum state of a quantum field looks calm because all the little fluctuations cancel in a symmetrical way. Near a black hole, that symmetry is broken by the horizon. Modes of the field that cross the horizon and connect inside and outside are not accessible to a distant observer. When you mathematically trace over the part of the field hidden inside and look only at the outside, the result is a state that has a temperature. It is as if the horizon has turned what one observer would call nothing into what another observer must interpret as a warm glow. Temperature is familiar on the scale of kitchens and weather, but here it plays a deeper role. In ordinary thermodynamics, a hot object is one whose microscopic degrees of freedom are jiggling more energetically than those of a cold one.
Hawking found that a black hole has an effective temperature tied to its mass and its surface gravity, the strength of gravity at the horizon. In words, the smaller the mass, the stronger the gravity at the edge, and the higher the temperature of the radiation. Giant black holes are colder than small ones. That result fits beautifully with an earlier insight from Jacob Bekenstein. He had been thinking about what happens to entropy when you drop something messy, like a box of gas with a complicated arrangement of particles, into a black hole. Entropy is a measure of disorder, or, more precisely, of how many microscopic configurations correspond to the same macroscopic state. The second law of thermodynamics says that in a closed system, total entropy never decreases. If the box disappears behind the horizon, its entropy seems to vanish from the universe we can see. To rescue the second law, Bekenstein proposed that black holes themselves must have entropy, and that their entropy is proportional not to their volume, but to the area of the event horizon. Every time you drop something in and make the black hole bigger, you increase that area and therefore its entropy. The horizon acts like a one-way memory surface. It hides the details from us, but its growth keeps track of the fact that there are more internal configurations than before. At the time, this idea was bold, even speculative. Hawking's discovery that black holes radiate with a definite temperature locked it into place. Thermodynamics tells us that if an object has both a temperature and an entropy, those two quantities must be related in a very specific way. Hawking's temperature and Bekenstein's entropy fit that relationship perfectly. Together, they show that black holes are not just holes, they are thermodynamic systems. They obey the same kinds of laws that govern steam engines, refrigerators, and hot stones cooling beside a fire. In a strange way, black holes may be the most perfect objects in the universe for teaching us about the deep connection between information, energy, and geometry. There is another twist. Most familiar systems have positive heat capacity. When they lose energy, they cool. When they gain energy, they warm. A black hole behaves in the opposite way. As it loses mass through Hawking radiation, it becomes smaller. As it becomes smaller, its temperature goes up. That means that the more energy it loses, the hotter it gets, and the more energetically it radiates. This feedback loop makes the final stages of evaporation, far in the future, violently quick compared with the earlier, slow leaking phase. You can think of this like a strange campfire that burns faster as it runs out of fuel. In the beginning, when the logs are whole, the fire smoulders. As the logs shrink, the flames grow brighter instead of fading. Near the very end, the last bits flare up suddenly and vanish. For a black hole with the mass of a star, the smouldering phase would last an incomprehensible length of time, far longer than the current age of the universe. Only in the final tiny fraction of that life would the hole shine with anything like intensity. On the scale of our universe today, Hawking radiation from known black holes is drowned in background noise. The cosmic microwave background, the afterglow of the Big Bang, bathes everything in a faint, uniform warmth. Stellar and supermassive black holes are colder than that. They absorb more energy from this cosmic bath than they emit. They are still growing, or at least maintaining their mass, not yet shrinking. Only when the universe has expanded and cooled for trillions upon trillions of years will the background temperature fall below that of these black holes and allow evaporation to dominate. There is one intriguing possibility where evaporation might matter sooner.
Some theories suggest that very small black holes could have formed in the early universe through density fluctuations, long before stars existed. These primordial black holes would have had a wide range of masses. The smallest ones would have already evaporated by now, releasing their energy in a final burst. Larger ones might still be around, shedding mass slowly. People have searched for signs of those final bursts in gamma-ray data, looking for sudden flashes that would match the predicted signature of a dying black hole. So far, no convincing evidence has emerged, but the search continues. Even without a direct detection, the logic behind Hawking radiation has become a cornerstone of theoretical physics.
It ties together quantum mechanics, thermodynamics, and general relativity in a way that is hard to dismiss as coincidence. Still, there is an understandable desire to see the underlying ideas tested in more accessible settings. That is where analog horizons come in. If you cannot build a real black hole in a lab, you can try to create systems that mimic the way horizons block waves. One such system uses a flowing fluid or a Bose-Einstein condensate, a state of matter where many atoms act together in a single quantum wave. If you arrange the flow so that it moves faster than the speed of sound in some region, then sound waves trying to climb upstream from that region are swept back. There is a point in the flow where the water speed, or the condensate speed, matches the speed of sound.
Beyond that point, no sound can escape. This is a sonic horizon. Calculations show that quantum fluctuations in such a medium should create pairs of phonons, the sound equivalent of particles, in a pattern very similar to Hawking radiation. Experiments along these lines have observed subtle correlations in the noise that look like pairs of phonons being created near the horizon, with one falling in and the other escaping. The details are still debated, and no single experiment has ended all arguments. But the fact that entirely different physical systems can reproduce the key features of Hawking's calculation suggests that the underlying mechanism is robust. It is not a fragile quirk of a particular model, but a general property of horizons and quantum fields.
All of this helps address one lingering worry you might have had. If nothing escapes from inside the event horizon, how can a black hole radiate? The important point is that the radiation comes from outside the horizon, from the rearrangement of the quantum fields in the curved spacetime around it. No particle climbs out from the interior. The one-way nature of the horizon remains intact locally. The leak is a global effect, a rebalancing of the field's energy as it adjusts to the presence of the horizon. The black hole pays for this adjustment with its mass, which is why it slowly shrinks. There is a subtle beauty in that picture. The same geometry that makes the horizon a point of no return also reshapes the vacuum in a way that gives rise to the radiation.
The event horizon is both a gate that nothing crosses outward and a kind of catalyst that changes the behaviour of the surrounding fields. In that sense, The boundary between inside and outside is not just a passive divider, it is an active player in the energy bookkeeping of the universe. At this stage, it is natural to take a step back and ask what is really fundamental here. Are we looking at matter acting on space-time, which then feeds back through quantum fields, or is the curvature itself the main actor, and matter a kind of secondary effect? Hawking radiation can be read as a hint that the geometry is doing more than just responding to mass. It is actively shaping what counts as energy and particles for different observers. The horizon is not just telling matter where to go.
It is helping decide what matter is. That is a dizzying thought. It suggests that our intuitive hierarchy, where solid stuff feels real and the invisible geometry feels like a useful bookkeeping device, might be backwards. Maybe the geometry and the information encoded in it are the most basic parts of the story, and what we call matter is more like a pattern that emerges when that geometry is viewed in a certain way. This is where ideas like the holographic principle come in, hinting that the information content of a region might be stored on its boundary rather than in its volume. We will not dive fully into those advanced theories here, but they all trace back in part to the realization that a black hole's entropy is proportional to its surface area, and that its evaporation is driven by the structure of spacetime at the horizon. The more you stare at that area, the more it looks like the real protagonist. The matter that fell in might just be the footprint. The curved spacetime might be the foot. To explore that possibility, we need to look more closely at what it really means to move freely in a curved spacetime, and at why objects in orbit around a massive body resist falling straight in. Only then can we see how the supposedly simple act of falling around a black hole turns into a complex dance of energy, information, and geometry that challenges our sense of what is real and what is only a shadow. If you want to see that dance with your own intuition, imagine you are inside a small, windowless room floating in deep space. The engines are off. You let go of a ball and it hangs beside you, motionless. You feel weightless, not because gravity has vanished, but because nothing is pushing on you. Now picture the same room in freefall near a planet. If the room and everything in it are falling together, the ball will once again float weightless by your hand. Your body cannot tell whether you are drifting in empty space or plummeting down a gravitational well.
That is the clue Einstein followed. He realized that the feeling we call weight is not caused by gravity itself. It is caused by the flaw preventing you from following the path gravity wants you to take. When you stand on Earth, the planet is constantly pushing you upward ever so slightly to keep you from falling toward its center. Your natural path would be to fall. The flaw interrupts that path. In orbit, that interruption disappears. You and the spacecraft follow the same curved path through space-time. You feel light, not because there is no gravity, but because nothing is resisting it. This idea becomes concrete if you think about a satellite. Imagine firing a cannonball horizontally from a high mountain. Fire it gently and it arcs down and hits the ground. Fire it faster and it travels farther before hitting. There is a particular speed at which the curvature of the ball's path matches the curvature of the Earth's surface. At that speed, every time the ball falls, the ground curves away beneath it just enough that it never hits. It misses the ground over and over again. That is an orbit. It is continuous free fall that never quite arrives. From the point of view of space-time, the satellite is simply following a geodesic, the straightest available path in the curved geometry created by Earth's mass. There is no mysterious sideways force holding it up. There are only initial conditions and the shape of the landscape it moves through.
Inside the satellite, astronauts float, not because Earth's gravity is gone, but because both they and the walls are falling together along that same geodesic. The straight line of their experience is a curve in the coordinates we draw on the universe. The deeper lesson is that motion is always relative to the background geometry. In a flat space-time with no masses, geodesics are simple straight lines that go on forever. Introduce a massive body, and those geodesics bend inward. Introduce an extremely dense body, and the bending becomes so extreme that the inward curves close off completely. Within a certain region, Every possible geodesic leads inexorably toward the center. The event horizon is the boundary of that region. Outside, some paths go around, some go away, some fall in.
Inside, every path dives deeper. Once you see gravity as geometry, another question emerges. If objects naturally want to follow geodesics, why do they so often refuse? Why does matter end up in stable orbits instead of plunging directly into the central mass? The answer lies in angular momentum, the measure of how much something is rotating or moving around something else. Whenever matter has sideways motion, that motion resists being redirected straight inward. It wants to keep going around. Your intuition already knows this from spinning on a playground roundabout or watching a skater pull in their arms and spin faster. If you throw a stone straight up, it rises, slows, and falls back. If you throw it at an angle, it follows a curve.
Give it enough sideways speed and that curve misses the ground. The same is true on larger scales. Gas clouds swirling through a galaxy rarely head perfectly straight toward the central black hole. They bring with them a mix of inward and sideways motion. Some fragments are deflected into wide orbits, others graze closer, lose a bit of angular momentum, and settle into tighter paths. It takes effort for matter to actually fall in. Something has to carry away its excess angular momentum. Around a black hole, that effort is carried by the accretion disk. Each ring of gas in the disk tugs on its neighbours through gravity, friction, and magnetic fields. Inner rings give some of their angular momentum to outer rings. The inner gas moves inward, falling to lower, faster orbits and heating up. The outer gas moves outward, taking that rotational energy with it. The disk is not just a feeding mechanism, it is a machine for moving angular momentum around so that some matter can spiral inward while other matter is flung away. This is why you sometimes hear that it is hard to hit a black hole directly. To fall straight in from far away, you would need to aim with almost impossible precision and cancel almost all your sideways motion. Miss by even a little, and you end up in some kind of orbit instead. The black hole is small compared with the space around it. The chance of a direct hit is tiny. Nature mostly delivers material with a mix of directions and speeds. The result is a complex, turbulent structure rather than a neat, simple plunge. If you could float above such a disk and watch, you would see a balance of order and chaos. On average, the gas circles the hole in smooth rings. Locally though, turbulent eddies, magnetic twists, and shock waves rip through the flow. Energy is dissipated into heat. Some of that heat is radiated away as light. Some is carried off in winds or jets. A tiny fraction of the matter crosses the last stable orbit and begins its final drop inward. In that region, there is no longer any orbit that lasts. Every path curves down toward the horizon. This behavior suggests another way to think about reality. Instead of starting with solid objects and then asking how they move, we can start with the geometry and the allowed paths, and ask what kinds of objects can follow those paths. In this view, planets, stars, and even human bodies are patterns of energy and momentum, arranged along geodesics and interacting through fields. Mass and matter become shorthand for stable bundles of those patterns. The question of whether curvature comes from mass or mass comes from curvature becomes less clear-cut. One evocative analogy is the footprint in sand. When someone steps on the beach, their foot presses into the grains and leaves a depression. The shape of the footprint tells you something about the foot that made it, even if the person is long gone. Now imagine that you only ever see footprints, never the feet themselves. You might begin to describe the world in terms of patterns in the sand. You could even predict how new footprints will overlap and combine.
At some point, the question of whether the foot or the footprint is more real becomes tricky. In the black hole story, the mass that collapsed is like the foot, and the curved space-time is like the footprint. Traditionally, we say the mass creates the curvature. Yet Hawking radiation flips the arrow. Changes in the curvature near the horizon give rise to a flow of energy that alters the mass. The footprint is feeding back on the foot. That has led some physicists to wonder whether space-time geometry and information are in fact the deeper entities, and what we call matter is a way those entities appear when we zoom in on certain scales. Relativity encourages that shift in perspective. It tells us that what we perceive as a gravitational force is really our resistance to following geodesics. It blends space and time into a single four-dimensional fabric where no observer has a privileged view. It makes light cones and horizons, not solid objects, the primary structures. Quantum field theory, on the other hand, tells us that even what we call vacuum is a dynamic stage. Fields fluctuate, entangle, and exchange energy. When we combine the two, black holes become laboratories where geometry and quantum activity talk to each other loudly. One of the most provocative hints that geometry might store information in a deeper way comes from that area law for entropy.
If you take a region of space and fill it with some ordinary matter, you might expect that the maximum amount of information you can pack in would scale with the volume. More room means more places to store bits. Black holes defy that expectation. Their entropy grows with the surface area of the horizon. It is as if the information about everything that has fallen in is smeared across that boundary as finely as the laws of physics allow. This inspired the holographic principle, the idea that the information content of a volume of space might be fully encoded on a lower dimensional boundary, somewhat like a hologram encodes a three-dimensional scene on a two-dimensional plate.
In some theoretical models, a world with gravity inside can be mapped to a world without gravity living on the boundary. In those mappings, what looks like curved space-time and falling matter in the bulk becomes patterns of quantum fields on the surface. The roles of foot and footprint start to blend. We do not yet know whether our universe is truly holographic in that sense. Many of the most concrete examples live in simplified models, not in a full match to our cosmos. Still, the fact that black hole entropy behaves like a surface quantity rather than a volume quantity is hard to ignore. It is a numerical shout that boundaries matter more than we might have thought. The event horizon is no longer just an invisible shell where escape fails.
In the real universe, matter does fall, disks do form, and black holes do sit at the hearts of galaxies, shaping the lives of stars. Geometry and mass are not competing. They are two sides of the same coin. Yet when Hawking radiation allows curvature to bleed energy back into the wider cosmos, and when black hole entropy scales with area, the balance seems to tip. The coin itself may be geometry, with matter as patterns etched into its surface. You might feel a tension here between two intuitions. One says that the stone in your hand, the chair under you, the atoms in your body are the true building blocks. The other whispers that the deeper story is in the invisible structure that tells those atoms how to behave. Black holes are where that whisper gets loudest.
They are places where the rules simplify and intensify enough that we can glimpse the underlying logic. A small set of parameters, mass, spin, and charge, defines the object. Its horizon area tracks its entropy. Its slow evaporation speaks in the language of quantum fields. We have mostly talked about non-rotating black holes so far, ones that do not spin. That has kept the geometry simple. Real black holes almost certainly rotate. They inherit spin from the stars and gas that formed them, and as matter falls in, it can transfer angular momentum to the hole itself. When you add rotation to the picture, the geometry becomes more intricate. Space-time near the hole is dragged around with it. Paths that were simple circles become twisted spirals.
New regions appear where the very definition of standing still breaks down. This phenomenon, known as frame dragging, takes the idea that geometry is active to a new level. In a rotating space-time, even if you try to hover at a fixed position relative to distant stars, The local structure of spacetime insists on carrying you around. There is a region outside the event horizon where this effect is so strong that nothing can remain at rest relative to infinity. To understand what that means and what it allows, we have to leave behind the simple well picture and think of black holes as cosmic whirlpools, twisting not water but space-time itself. Picture a whirlpool in a river, a spinning funnel where the water drags leaves and twigs into a circling dance before pulling them under.
A rotating black hole is like that, except the whirlpool is not made of water, it is made of space-time itself. The hole does not just sit there twisting in the dark. As it spins, it drags the very fabric of the universe around with it. If you try to stay still nearby, space-time quietly refuses and nudges you into motion. This effect is called frame dragging, and it is not unique to black holes. Any rotating mass warps space-time in such a way that nearby inertial frames are twisted around the axis of rotation. Earth does it too, but so weakly that it takes exquisitely sensitive satellites and years of data to measure the tiny precession it causes. Near a spinning black hole, the effect is enormous. Instead of a gentle twist, you get a hurricane of geometry. The closer you get, the more space-time insists that you rotate along with the hole. To understand what this means for an observer, imagine you fire your rockets and try to hover motionless over the spinning black hole, holding a fixed position relative to the distant stars. Far away, that is easy. Your engines balance the mild pull of gravity and you sit still. Closer in, the story changes. The dragged space-time wants you to rotate. To stay aligned with the distant universe, your rockets have to fight not just gravity but the twisting of the frame. Eventually you reach a region where no amount of thrust can keep you from being swept around. That region is called the ergosphere. It is a sort of atmosphere of dragged space-time that sits outside the event horizon.
Its shape is not a perfect sphere. Near the poles, where the rotation axis points, it touches the horizon. Around the equator, where the dragging is strongest, it bulges outward. The defining feature of the ergosphere is that every possible path for a physical object is carried around in the direction of the black hole spin relative to the distant stars. You can still escape outward from the ergosphere if you fire your rockets in just the right way, but you cannot stand still. Inside the ergosphere, the distinction between rotating and not rotating loses meaning. Everything rotates, even light is forced into this dance. You might expect such a region to be nothing but trouble, yet it opens a remarkable door. Because the frame is dragged so fiercely, there exist paths where a particle can fall in and end up with a kind of negative energy, as seen from infinity. That sounds impossible at first. Energy is supposed to be positive, but in curved space-time, energy is defined relative to the symmetries of the geometry, and here the symmetries are twisted. Roger Penrose realized you could exploit this twist. He imagined a spacecraft entering the ergosphere and splitting into two pieces. One piece is sent on a trajectory that falls through the horizon with negative energy, as measured by a distant observer. The other piece escapes to infinity with more energy than the original spacecraft had. From the distant point of view, the total energy is conserved.
The gain in the escaping fragment is balanced by a decrease in the black hole mass. The rotating hole has given up some of its stored rotational energy. This process, now known as the Penrose process, is not something we are likely to attempt with real rockets anytime soon. The precision and conditions required are extreme, but as a thought experiment it shows that a spinning black hole is not just a sink, it is also a potential source. Up to a significant fraction of its rotational energy can, in principle, be extracted by clever use of orbits in the ergosphere. That is a profound shift from the early picture of black holes as dead ends. You might ask whether nature runs any version of this process on its own.
The answer seems to be yes, through magnetic fields and plasma, rather than engineered spacecraft. Around many black holes, especially the supermassive ones in galactic centers, we see narrow jets of matter and energy blasting out along the rotation axis at close to the speed of light. These jets can extend for thousands or even millions of light years, carving out cavities in surrounding gas and lighting up radio telescopes with their glow. One widely studied idea is that these jets tap into the rotational energy of the black hole through magnetic fields that thread the ergosphere. The spinning spacetime twists those field lines, which in turn act on charged particles in the plasma around the hole. The process can channel energy outward along the field lines and launch matter into space.
In that picture, the jets are a natural, large-scale version of energy extraction, converting spin into directed beams that alter their host galaxies. Whether that exact mechanism is at work in every case is still under active research, but the broad point stands. A rotating black hole surrounded by magnetized plasma is not a passive bystander. It is a dynamical engine. Its spin and the dragging of space-time around it can power structures far larger than the event horizon itself. If you were looking for the ultimate cosmic power plant, you could do worse than a freshly fed, rapidly spinning supermassive black hole with strong magnetic fields. There is a temptation, whenever we talk about energy extraction in curved space-time, to wonder about tricks that might allow faster than light travel. The rotating black hole seems to offer possibilities. The way geodesics wrap around its spin axis, the frame dragging, the existence of regions where energy bookkeeping becomes strange, all of this invites speculation. Some exact solutions of Einstein's equations even suggest that, mathematically, paths through or around spinning black holes could link distant regions in ways that look like shortcuts. However, when you work through the physical details, nature is much less generous than the equations on paper might suggest. Many of the exotic routes that appear in ideal solutions are unstable or require conditions that cannot be met in a realistic universe. Any attempt to keep a traversable shortcut open tends to run into quantum effects, feedback, and the ordinary stubbornness of matter. The consensus among most physicists is that while black hole geometry hints at how space-time could allow effective shortcuts, it does not give us an off-the-shelf blueprint for a warp drive. That does not make the spinning hole less interesting. In fact, it makes it more valuable as a laboratory. It offers us a way to see how relativity handles extreme rotation, how energy and angular momentum are traded between matter, fields, and geometry, and how horizons behave in the presence of spin.
Think of it as the universe stress testing its own rules. By watching how black holes grow, spin down, and power their surroundings, we learn what is really allowed when gravity is pushed hard. To get a better feel for scale, consider the different families of black holes we have identified. Stellar mass black holes have a few to a few dozen times the mass of the Sun, and are born from collapsing massive stars or from mergers of neutron stars. Intermediate mass candidates bridge the gap between those and the giants, with perhaps hundreds or thousands of solar masses, though they are harder to pin down. Then there are the supermassive black holes, with millions or billions of solar masses anchoring the cores of galaxies. A spinning stellar mass black hole might have an event horizon only a few tens of kilometers across. A rapidly rotating supermassive black hole could have a horizon larger than the orbit of Mercury. Yet in both cases, the same basic principles apply. Spin drags spacetime, an ergosphere forms. Accretion disks swirl outside, fed by gas, stars, or whole clouds. The details differ in scale and environment, but the dance of geometry and matter plays to the same tune. In the vicinity of these objects, space-time becomes a sculptor. It carves out regions where light can loop in unstable orbits, where particles can hover in strange balanced paths, and where entire flows of plasma are steered into jets.
If you could hover at a safe distance and watch over many thousands or millions of years, you would see the black hole grow as it consumes matter, then gradually spin down as it sheds its rotational energy through radiation and outflows. Mass, spin, and charge, the simple parameters that define it, would slowly change under the influence of the matter and fields around it. This picture reinforces the sense that a black hole is as much process as object. It is a node in the cosmic network where gravity, quantum fields, and thermodynamics meet. Its rotation is not a trivial detail. It shapes how efficiently matter is swallowed, how brightly the accretion disk can shine, and how powerful any jets might be. Observations of X-ray spectra, iron lines broadened by extreme velocities, and timing variations in flickering disks all carry fingerprints of that spin. When astronomers talk about measuring the spin of a black hole, they are reading those fingerprints. They compare the observed spectra and timing patterns with models of how gas should behave in different space-time geometries. A rapidly spinning hole allows stable orbits closer to the horizon than a non-spinning one. Gas that orbits closer gets hotter and emits higher energy radiation. The inner edge of the disk, the shape of the broadened lines, and the pattern of variability together hint at how fast the central hole is turning. The fact that we can do this at all, that we can infer the spin of an invisible object many thousands or millions of light years away by studying the way light shifts and flickers, is a testament to how well the geometry-based view of gravity works. We take Einstein's equations, calculate how space-time should be shaped, simulate how gas moves in that geometry, and then compare with data coming from space observatories. When the match is good, it is hard not to feel that we are seeing something very close to the real engine at work. All along, the theme that started to emerge in the earlier parts continues here. What feels fundamental keeps creeping from matter toward geometry. The mass of the black hole matters, but largely because it sets the scale of the curvature.
No wonder so many modern ideas about quantum gravity and holography focus on understanding space-time itself as an emergent, information-laden structure. Yet for all their power and drama, even spinning black holes cannot act without something to feed on. Their accretion disks, their jets, their role as engines that light up galaxies, all of this depends on the messy, angular momentum-rich universe around them. Gas has to find its way inward from vast distances. Stars have to wander close enough to be shredded. Whole clouds have to be stirred and torqued until some fraction of their material spirals down to the waiting hole. The surprising truth is that this delivery process is often inefficient. The black hole may sit at the centre like a perfect drain, but most of the water in the cosmic bathtub circles, sloshes, and evaporates rather than plunging in. Gravity curves space-time, spin drags frames, but angular momentum pushes back, forcing matter into long, complicated journeys. Understanding how that tug-of-war plays out will tell us why some black holes blaze as quasars while others sleep quietly, and why, despite their fearsome reputation, it is much harder to fall in than you might expect. If you want to feel how stubborn angular momentum really is, imagine trying to drop a coin straight into the centre of a spinning record. Toss it from above, and almost every throw will land off-centre and send the coin skittering into a spiral path instead of a direct plunge. Space around a black hole works the same way, just with gravity and orbital motion instead of vinyl and friction. Matter almost never approaches in a perfectly straight line. It arrives with sideways motion, and that sideways motion is surprisingly hard to get rid of. That is why, on a galactic scale, you can pack millions or billions of stars and vast reserves of gas into the region around a central black hole, and still find that only a tiny fraction actually falls in. Most of the material orbits, collides, and drifts for eons. It is as if the universe keeps loading dice against direct infall. Whenever you picture a black hole as a hungry mouth swallowing everything nearby, it is worth remembering that most of the meal spends an astonishing amount of time circling the plate. To understand how anything ever makes it to the event horizon, you need to see the accretion disk not as a simple ring, but as a complex machine that trades angular momentum around. Think of cars on a multi-lane highway, where inner lanes move faster than outer lanes. If cars occasionally nudge each other and swap lanes, some will move inward and speed up, others will move outward and slow down. The total traffic energy is conserved, but its distribution changes. In a disk, gravity, turbulence, and magnetic fields play the role of those nudges. Each ring of gas orbits at a speed set by its distance from the black hole. Inner rings go faster, outer rings slower. When turbulence stirs them, the inner gas can lose a bit of angular momentum to the outer gas.
Losing angular momentum lets it drop to a slightly lower orbit, where it has to move faster. The outer gas gains angular momentum, drifts outward, and slows. This cascading exchange repeats over and over. Over long times, a small fraction of the gas is driven inward while a larger fraction is pushed outward and may never fall in at all. This process is often compared to viscosity, the internal stickiness that makes honey flow more slowly than water. In a real accretion disk, the apparent viscosity is driven not by molecules bumping into each other, but by tangled magnetic fields that link distant parts of the gas together. As the disk orbits, those field lines stretch and twist, transferring angular momentum across large distances. The result is a kind of magnetic braking.
Inner regions are braked and fall inward. Outer regions are spun up and move out. As gas moves inward, gravitational energy is released. The closer it gets to the black hole, the deeper the gravitational well it sits in. Each step down in radius converts potential energy into kinetic energy, and then into heat as particles jostle and collide. Near the inner edge of the disk, that heating is intense. Temperatures can reach millions of degrees. At those temperatures, atoms are stripped of their electrons, the gas becomes a plasma, and it glows fiercely in X-rays. The disk itself becomes a brilliant light source, powered purely by gravity and friction. What makes this remarkable is how efficient the process can be.
When you fuse hydrogen into helium in a star, you convert only a small fraction of the mass into energy. Accretion onto a black hole can be much more efficient. Depending on how fast the hole spins and how close the inner edge of the disk can orbit, something like 10 to a few tens of % of the mass energy of the infalling matter can be radiated away before crossing the horizon. That makes accretion disks some of the most efficient engines in the universe. You and I are used to engines that burn fuel, heat a working fluid, and drive pistons or turbines. Here, the working fluid is the gas itself, and the fuel is its gravitational potential. The more it falls, the more energy it can release. If you could somehow capture all the radiation from matter spiraling into a rapidly spinning black hole, you would get far more usable energy per kilogram than from any chemical process, and even from nuclear fusion in stars. It is a sobering thought that the universe builds such engines routinely, while we're still learning how to read their light. Sometimes, these engines shine so brightly that they outglow everything else around them. In the distant universe, astronomers found objects that looked like stars through small telescopes, yet were far too bright to be single suns. Their spectra showed wide emission lines shifted by enormous amounts, indicating that they lay at great distances and that their host galaxies were racing away with the cosmic expansion. To shine as brightly as they do from that far away, these quasi-stellar objects, or quasars, must release staggering amounts of energy. The best explanation is that quasars are galaxies whose central black holes are in a feeding frenzy. Vast quantities of gas, funneled in by galaxy mergers or violent instabilities, have formed thick, hot accretion disks around the central monsters. As matter spirals inward, the disks radiate across the spectrum, from radio waves to X-rays. In many cases, the luminosity from this tiny central region dwarfs the combined light of all the stars in the host galaxy. You're looking at a black hole-powered lighthouse that can be seen across billions of light years. From our vantage point, quasars serve as both beacons and probes.
They let us see deep into cosmic history, back to times when the universe was only a fraction of its current age, and galaxies were still assembling. Their spectra carry fingerprints of the gas between galaxies, letting us study how the cosmic web of matter has evolved. At the same time, they remind us that black holes are not just endpoints of stellar evolution, they are active participants in shaping galaxies, bathing their surroundings in radiation and outflows that can trigger or shut down star formation. In many active galaxies, we see something even more dramatic than bright central disks. We see jets, narrow beams of plasma and radiation shooting out along the poles of the spinning black hole. These jets can extend well beyond the visible extent of the galaxy, sometimes for millions of light years. They carve out lobes of radio emission where they slam into surrounding gas. Within the jets, particles are accelerated to near light speed and emit intense radiation as they spiral along magnetic field lines. The origin of these jets is still an area of active research, but a common picture has emerged. Magnetic fields anchored in the accretion disk, or threading the black hole itself, get twisted by the rotation. This twisting stores energy in the fields, like winding up a spring. Plasma near the black hole couples to those fields and is flung outward along the rotation axis.
The jets effectively drill through the surrounding material, escaping where the resistance is lowest, perpendicular to the plane of the disk. What matters for our story is what these jets and outflows do to the galaxy around them. They deposit energy and momentum into the interstellar medium. They can heat gas that might otherwise cool and collapse into new stars. They can push gas out of the central regions altogether. In some cases, this feedback may be what stops galaxies from growing unlimited numbers of new stars and keeps them from becoming far more massive than they are. The invisible geometry and accretion physics at the centre end up governing the visible fate of entire stellar cities. If you zoom out further, this becomes part of a larger ecosystem.
Gas flows into galaxies along filaments of the cosmic web. Some of that gas ends up forming stars. Some is blown back out by stellar winds and supernova explosions. Some finds its way to the central black hole, lighting it up as an active nucleus. The radiation and jets from that nucleus then heat and stir the surrounding gas, regulating how much more can cool and fall inward. The black hole and the galaxy co-evolve, their masses tracking each other over billions of years. This co-evolution raises a subtle point about our original question: why it is so hard to fall in. On the smallest scales near the horizon, angular momentum and accretion disk turbulence control the final plunge.
On larger scales, the struggle is to bring gas from galactic distances down to those inner regions in the first place. Galactic bars, spiral arms, and tidal interactions and galaxy mergers can all torque gas and drain away its angular momentum. Without those grand-scale disturbances, most gas would remain in wide orbits, forever circling but never reaching the central drain. You can think of this as a sequence of locks in a canal. Each lock drops the water a little lower, but you need a whole chain of them to bring a ship from a high lake down to sea level. Each step requires some mechanism to move angular momentum and energy around.
In space, those mechanisms are the collective gravitational fields of many stars, the shocks in spiral arms, the chaos of mergers, and finally, the magnetic storms in the accretion disk. Only when all these stages line up does a significant flow reach the black hole. Yet even then, not everything that approaches is consumed. Some of the gas that spirals in is redirected into winds that blow off the disk. Some joins the jets. Some heats surrounding gas so much that it expands and escapes the central region. The result is that black holes grow in fits and starts, with bright active phases followed by quieter times. They gain mass, lose spin, and rewrite their surroundings in cycles that can last millions to hundreds of millions of years.
From the perspective of a single human lifetime, all of this is impossibly slow. From the perspective of the universe, it is a dynamic equilibrium. Black holes do not simply sit at the centres of galaxies as static anchors. They act as engines and regulators. Their presence shapes star formation histories, galactic morphologies, and even the temperature of gas in clusters of galaxies. If you trace the story of cosmic structure forward far enough, you keep running into black holes as both consumers and influencers. One more puzzle sits in the background of all this. If black holes are so central to the lives of galaxies, and if they can in principle evaporate through Hawking radiation, what role will they play in the ultimate fate of the universe?
Will they end up locking away most of the mass only to slowly leak it back as a thin bath of low-energy particles? Will the information about what fell in be forever inaccessible, or is it somehow woven into the outgoing radiation in a way we have not yet fully decoded? Those questions reach beyond the glowing disks and the visible jets into the deep future. They connect the messy astrophysics of accretion with the abstract puzzles of quantum information and the long-term evolution of the cosmos. To follow them, we have to leave behind the noisy, gas-rich universe of young galaxies and picture a much older, quieter cosmos in which black holes, rather than stars, are the dominant players in the remaining drama.
To picture that older, quieter cosmos, imagine pressing fast forward on the universe. The bright, messy present with its blue spirals, exploding stars, and glowing nebulae slowly fades. Star formation, which today still stitches fresh suns from cold gas, declines as the raw material is used up or heated. Galaxies that were once rich in gas become dominated by long-lived red stars. Their disks puff up and settle. In their centres, the black holes we have been following keep quietly gaining mass, merger after merger, meal after meal. We already see hints of this long arc by looking far away, which also means far back in time. When we point our telescopes to great distances, we are sampling an earlier universe. There, quasars explode into view, far more common than they are close by.
Their light journeys across billions of light years to reach us, carrying a snapshot of a wilder era when gas was plentiful and central black holes fed greedily. Closer to home in both space and time, most galaxies are quieter. Their central black holes still exist, but many are on a diet. Our own galaxy is a good example. At its heart lies Sagittarius A star, a supermassive black hole with a mass of a few million suns. On human timescales, it is sleepy. Occasionally it flares a bit, but there is no giant quasar-like beacon. Yet by tracking the orbits of nearby stars, we know the mass that sits in that small central volume. Their paths whip around invisible nothing, making sharp turns that reveal a concentrated gravitational pull.
In the past, when the Milky Way was gas-rich and still assembling, that central hole likely shone more fiercely. Other galaxies host far larger monsters. Some harbour black holes weighing billions of solar masses. One of the most extreme known lies in a quasar called TON 618, whose central engine appears to be tens of billions of times more massive than the Sun. Its accretion disk blazes so brightly that from our vantage point it outshines entire clusters of ordinary galaxies. These giants push our intuition. What physical process can assemble so much mass into such a small region? And how does the surrounding galaxy survive such a powerful neighbour? Part of the answer lies in how we find these objects.
There is a selection effect known as Malmquist bias, named after the astronomer who studied it. Roughly speaking, when you survey a population of distant objects with a fixed telescope sensitivity, you are more likely to detect the brightest members than the dim ones. At great distances, only the most luminous quasars stand out strongly above the noise. Those are the ones with the most massive and vigorously feeding black holes. Closer to home, we can see weaker active nuclei and quiet cores that would be invisible at larger distances. This bias can trick our intuition if we are not careful. Looking only at the distant bright sample, we might think that enormous, violently active black holes dominate the universe. Looking only at our cosmic neighbourhood, we might think most central black holes are modest and idle. In reality, both extremes exist, along with a continuum in between. The population has evolved over time. The universe had a quasar-heavy adolescence, when gas supplies were fresh and easy to funnel inward. Now it is partway into middle age. The most dramatic growth phases are rarer. Despite all this variety, we find a surprising order in the statistics. When astronomers measure the masses of central black holes in many galaxies and compare them with properties of the galaxies themselves, tight relationships emerge. One famous relation connects the black hole mass with the random speeds of stars in the galactic bulge, the central swarm of old stars.
Galaxies with more massive bulges and faster-moving stars tend to host more massive black holes. That correlation suggests that black holes and their host galaxies do not grow independently. They co-evolve. Feedback from accretion helps enforce this co-evolution. When the central hole is fed too quickly, its disk and jets pump out radiation, and outflows that can heat or expel gas from the central regions. Star formation slows, the supply of fresh fuel dwindles, the black hole's growth stalls. Later, as gas cools and drifts back in, a new feeding episode can begin. Over billions of years, this push and pull steers galaxies onto the observed relationships. The small region near the event horizon, where geometry and quantum fields are at their most intense, ends up influencing structures tens of thousands of light years across. If we wind the cosmic clock forward instead of backward, we expect that influence to continue. Stars will keep living and dying. Some will collapse into new black holes. Others will be shredded as they stray too close to existing ones. Galaxies will merge, and when they do, their central black holes will sink toward the merged core, orbit one another in a slow dance, and eventually spiral together, emitting ripples in spacetime called gravitational waves as they coalesce. Each merger builds a larger, heavier black hole at the center of the new galaxy.
Over immense timescales, much of the matter that is currently in stars may end up either in white dwarfs, neutron stars, or black holes. White dwarfs can cool and crystallize into cold remnants. Neutron stars can remain, collide, or collapse further. Black holes will swallow some fraction of both. In dense environments like star clusters, interactions can preferentially sling lighter objects away and drive heavier ones inward. That means black holes, which are the densest and most massive compact remnants, tend to sink toward the center and grow even more dominant over time. Cosmologists sometimes sketch a far future era they call the black hole age. In that phase, almost all luminous star formation has ceased. Long-lived red dwarf stars still burn slowly, but the universe is dimmer.
The main gravitational actors are black holes of various masses. They orbit, merge, and reshape their surroundings, but the overall trend is toward fewer, more massive holes separated by larger stretches of mostly empty space. It is a quieter, darker universe than the one we see now. Even that is not the end of the story, because Hawking radiation quietly waits in the wings. As the universe expands, the relic glow of the Big Bang cools. The background temperature falls. Trillions of years from now, it will drop below the incredibly low temperatures associated with Hawking radiation from large black holes. At that point, the balance flips. Instead of absorbing more energy from the cosmic bath than they emit, black holes will begin to lose energy on net.
They will enter a true evaporation phase. The timescales involved are staggering. A black hole with the mass of the Sun would take an almost unimaginable length of time to evaporate, far outstripping the current age of the universe. A supermassive black hole with millions or billions of solar masses would take far longer still, numbers that make human history and even the lifetimes of stars look like instants. During most of that long decline, the Hawking radiation would be cold and feeble, a thin drizzle of low-energy particles seeping into an already sparse cosmos. As each black hole shrinks, its temperature goes up and the rate of radiation increases. The final stages, when the hole has lost most of its mass, would be relatively rapid.
For a tiny primordial black hole, that final moment might look like an intense flash of gamma rays. For the behemoths at galactic centers, the flare-up would happen so far in the future that everything familiar would be gone. There would be no galaxies left to light, no nearby observers to watch. The universe would be deep into its long twilight. What remains after all black holes have evaporated is a matter of current research and debate. The standard picture from classical general relativity and simple quantum field arguments is a cold, dark universe filled with a dilute gas of low energy, particles and photons expanding forever. No new structures form, no engines run. It is a state sometimes called heat death, not because it is hot, but because useful gradients of energy have been erased. Everything is as spread out and even as it can be. Yet even in that quiet endgame, the puzzles raised by black holes do not fully go away. The question of what happens to information that fell into a black hole remains one of the deepest in theoretical physics. Does the Hawking radiation carry a subtle, scrambled imprint of everything that went in, preserving information at a level that is incredibly hard to decode but not lost? or is information genuinely destroyed, forcing us to revise long-held beliefs about how quantum mechanics works? Or is there some third option, involving new physics at the horizon or in the final burst that we have not yet grasped?
Different ideas compete. Some suggest that the interior of a black hole is connected by unseen shortcuts in spacetime to other regions, making the bookkeeping more complex than it appears. Others propose that the horizon is not a simple, smooth surface at the quantum level, but a seething structure that stores and re-emits information in ways we are only beginning to model. The holographic principle offers one route, hinting that everything that ever fell in might be encoded on the horizon and then gradually released in the outgoing radiation as the area shrinks. From our vantage point as curious observers in a young universe, we do not yet know which of these pictures is closest to the truth.
What we do know is that black holes have forced us to connect ideas that once lived in separate boxes. Gravity, quantum theory, thermodynamics, information, and cosmology all collide in these objects. They were born in the equations as curiosities and once thought of as endpoints, simple products of collapse. Now they sit at the centre of many of our biggest questions. There is a certain irony in that. Black holes hide everything that crosses their horizons from direct view, yet by watching how they tug on stars, how they light up accretion disks, how they launch jets, and how they shimmer in gravitational waves when they collide, we have learned more about the workings of gravity and space-time than we ever could have from gentler systems.
Their apparent simplicity, mass, spin, and charge, defining everything, hides a rich internal bookkeeping that we are still trying to decode. In a way, the journey we have taken mirrors the journey of physics itself. We started with the idea of a one-way door, a region from which nothing returns, carved out by the collapse of massive stars. We learned to see that door not as a solid wall, but as an invisible boundary in geometry, marked by strange behaviour of light and time. We discovered that the space around it is full of structure, from photon spheres and ergospheres to roaring accretion disks. We saw how quantum fields refuse to stay quiet even there, pulling a faint glow from the curvature. Along the way, our sense of what is fundamental shifted.
Matter began to look less like a collection of independent building blocks and more like patterns in fields guided by geometry. Entropy migrated from volumes to surfaces. Energy accounts had to include contributions from the vacuum itself. The universe, seen through the lens of black holes, started to look less like a stage filled with actors, and more like a web of relationships between geometry, information, and motion. You might find that unsettling or exhilarating, or both. On the one hand, the thought that even the most solid objects and the brightest galaxies are just temporary patterns in a deeper structure can make everyday life feel fragile. On the other hand, it means that the laws we are uncovering here connect us to everything.
The same equations that describe a falling apple, a circling satellite, and a whisper of Hawking radiation also describe the grand arcs of galaxies and the eventual fate of the cosmos. Standing under our ordinary sky, none of this is visible. The stars look still, the Milky Way arches softly overhead. Somewhere in that calm band of light, our central black hole turns, too faint to see, its accretion trickle currently thin. Far beyond, quasars blaze and fade. Far ahead, black holes will rule a quieter universe before giving their energy back to the void. We occupy a fleeting, bright moment between those eras, with just enough tools and curiosity to glimpse the full arc. The next time you think of a black hole, you can picture more than a dark sphere that eats everything.
You can picture a region where geometry takes charge, where time slows, where light loops and hesitates, where quantum fields hum and occasionally let a particle slip away, where rotation drags the very coordinates of reality into a whirl. You can picture them not only as endings, but as engines, regulators, storytellers of the universe's past and its possible futures. And somewhere in that picture, you can place yourself, a brief pattern of fields and geometry, wondering how all of this fits together, listening in as the universe uses its darkest objects to reveal some of its brightest secrets.